Oceanographers are facing a challenge in trying to understand ocean currents. Until recently, our knowledge of ocean currents came from a few widely spaced measurements made all over the oceans over many years. But then physical oceanographers got together to have a look at the ocean on a smaller scale.
At the same time. And we ought to draw vertical lines through those, where, where the profiles are things
1973 Bermuda. A group of scientists headed by Henry Stommel meet to discuss the mid-ocean dynamics experiment, or MODE for short. Among them is Walter Monk, who talked to us about the experiment.
The MODE expedition was the most ambitious undertaking of its kind. A certain volume of ocean was selected, 200 by 200 kilometers, from top to bottom, and then the hell was instrumented out of this volume.
MODE was a combined British-American effort in which the latest in ocean technology was put to work, much of it for the very first time. But what were these instruments looking for? Putting it simply, they were looking for weather, not in the atmosphere, but in the deep ocean. But how good is the parallel between atmosphere and the ocean? We're familiar with the atmosphere, so let's look at that first. This is the world's wind system, a climatic map. From it, it looks like the British Isles are being constantly subjected to southwesterly winds. But as you know, the wind system for a particular day can be totally different from this. These pressure contours in the North Atlantic show the resultant wind directions for a day in November. It's clear that the wind over Britain is blowing from the northwest. This sort of situation is not hinted at in the climatic map. Over the course of 2 weeks, the pattern develops as highs and lows sweep through the area, causing the wind direction to vary from day to day, giving us weather as opposed to climate. But if the wind data were averaged over the whole year, we'd be back to the southwesterly pattern of the climatic map. MODE scientists believe that our wind system provides a useful analogy to currents in the ocean. If they wanted to find the equivalent of weather in the ocean, like meteorologists, they would have to make observations on a day-to-day basis in a relatively small area. And this is the area they chose. A circle 200 kilometers in radius, in water depths of 4 to 5 kilometers. This approach was very different to the traditional one.
Until about 10 years ago, what we really did in oceanography in studying currents, you might classify as climatology. It was attempting to give the average state, and by average we mean really a very long time average, like a 10-year average. And then one spoke basically of 2 types of circulations. The relatively shallow ocean circulation, which is driven by the wind, and the very deep circulation, which is the result of density currents associated with water masses formed usually at very high latitudes.
Well, this is the surface circulation pattern, which shows the long-term averages or climatic averages that Walter Monk was talking about. And we know this is basically caused by the movement of winds over the surface of the ocean. Here's a wind-driven gyre in the Atlantic with the narrow Gulf Stream on the western side. And here's another one in the Pacific. And these gyres have intense western boundary currents along their western edges. Well, that's the surface circulation. Let's go and look at what's happening further down. And this map shows what we think the bottom circulation looks like. It isn't as detailed as the surface pattern, and sometimes it's in the opposite direction. For example, here, under the Gulf Stream, the bottom current is flowing from north to south, which is in the opposite direction to the Gulf Stream direction. And we know this pattern of deep circulation is basically caused by differences in density of water masses. It was Henry Stommel who first suggested that the water masses sink in their source regions and flow along the western sides of the oceans in an intense current, and then is carried back on the eastern side of the oceans in a much broader flow. It also rises through the thermocline and mixes with the surface waters. Well, the fact that this is less detailed than the surface pattern shows us that we don't know so much about what's going on down here. And it's only recently that we've been able to look at the deep ocean circulation on a longer time scale. But how did oceanographers find out what was going in the deep ocean before this? Well, one way they were doing it was to look at density measurements. And these were obtained from temperature and salinity data. Here's a temperature section in the Atlantic. We're going to use this method to look at what's happening to the surface currents, as we know what the answer is there, though it also applies to the deep ocean. The lines of equal temperature, the isotherms, slope gently up to the south, and when the effect of salinity is taken into account, we find the lines of constant density, the isopycnals, do something quite similar. The sea surface slopes in the other direction, shown here very exaggerated, so lines of equal pressure, the isobars, run like this. And because these sets of lines aren't parallel, this is a baroclinic condition. The isobars give a pressure gradient force to the south. Because this region is more or less in geostrophic balance, the current must flow to allow the Coriolis force to just balance the pressure gradient force. And this means that the current must flow from east to west, which is consistent with our knowledge of the Atlantic gyre. It was partly by this type of reasoning that oceanographers were able to deduce the nature of deep currents before technological advances made direct measurement of currents possible. As you know, the Earth's rotation is an important factor that affects the circulation pattern. The effect of this is a bit hard to visualize, so we're going to show you how this works. Here's a pendulum. Now watch what happens to the plane of swing of the pendulum bob as I rotate this turntable. It tends to keep vibrating in the same plane, although the base itself is rotating. So the swing of the pendulum bob doesn't appear to know what the base is doing. We say that the swing of the bob is only loosely coupled to the pendulum base. So here we have a device which shows up rotation about this axis. That's straightforward on a turntable. And let's have a look at it on a globe. I'm going to put it on the North Pole. I'll swing the pendulum. Then I'm going to rotate this globe through 90 degrees anti-clockwise. And watch what happens to the plane of swing of the bob. As you'd expect, it tends to keep vibrating in the same direction. But what would that look like if we were looking at it from the Earth itself? I'm going to repeat this, and this time we'll watch it from a camera moving round with the globe. The swing of the bob appears to rotate clockwise because the bob tends to keep vibrating in the same plane. But also notice how far it's rotated. It's rotated through 90 degrees, the same amount as the globe, but in the opposite direction. Now, I'll move the pendulum down to the 60-degree line of latitude, and we'll repeat it. Again, the camera is following the globe around, and this is what it would look like to observers on the Earth. The pendulum bob still has a relative clockwise rotation, but look at the angle. It's only moved through 45 degrees this time, half the value at the pole, although the globe has still rotated through 90 degrees. And this is because that the pendulum support is no longer in line with the Earth's rotation axis. So it's only got a component of the Earth's rotation. Rotation about this axis is less. Well, finally, I'll move the pendulum down to the equator. We'll have a look at the rotation there. Again, the camera is moving round with the globe. This time, the pendulum bob doesn't appear to rotate at all. And this is because the support now has no component of the Earth's rotation. So, in moving from the North Pole to the equator, the component of rotation about this axis has decreased. And as we know that vorticity is associated with rotation, in moving from the pole to the equator, the vorticity decreases. Or if we move north from the equator, the vorticity is increasing. And it's this increase in vorticity as we move north which causes the intensification of western boundary currents. Well, we hope this has clarified some of the more difficult ideas on ocean circulation. These form the cornerstones of our theories of ocean circulation, and it came as a surprise to the majority of physical oceanographers that there was more to it than that.
This somewhat blissful picture of a simple and smooth average ocean circulation was interrupted about 10 years ago when John Swallow dropped his current floats from the ship Ares and found that they didn't behave at all as anyone expected. Instead of moving at a very slow, steady velocity in one direction, they moved much more rapidly in another direction. And moreover, another float, which was only 20 kilometers away, I think, and which was supposed to have done the same thing, decided to go in a quite different way. And everybody was aghast that the ocean should have these nonconformist, complicated features.
These are the tracks of these neutrally buoyant floats as they drift around in the deep water. They're anything but uniform. And it was this that led to mode. John Swallow, on board the Discovery, took part. In the chart room, he talks about those early days aboard the Ares.
I had this idea at the time, you know, of getting another check on Henry Stommel's circulation model, where he was predicting that the deep water away from the boundary would move back towards the poles.
With a gentle sort of upwelling.
Yes, whereas all the southward motion in the deep water would be carried in the western boundary current. And whereas the traditional view was that you'd get a slow southward drift all the way across.
Like a lot of science, we start off looking for one thing, yet find another, completely unexpected. Swallow's voyage on the Ares was just like that. These floats are designed to sink slowly to a predetermined depth, where they become weightless or neutrally buoyant. As the currents sweep them around, their paths are acoustically tracked from the ship. Hanging from the lower end and just dangling in the water is the ballast weight and explosive release. When the release is fired, the weight falls away and the float returns to the surface and is picked up by the ship. Off it goes and the experiment is underway. But Swallow floats weren't the only floats to take part in mode. The Americans used their sound fixing and ranging floats, or SOFAR floats for short. SOFAR floats are designed to be heard hundreds of kilometers away, and to achieve this they make use of the sound channel. They're much larger than the Swallow floats and can work continuously for many months. Their characteristic hoots are emitted by the two resonant pipes on either side of the main tube, a sound similar to that made by some whales. Like Swallow floats, they're neutrally buoyant. In air they weigh almost half a ton, but on the surface they weigh a mere 6 pounds, and as they sink, they eventually become weightless. Each float is tuned to a different frequency, The distinctive hoots are received by hydrophones in the sound channel, which are linked to shore-based listening stations. The fix is calculated by measurements of the time delays in receiving the float's signal at different stations. So no ship is required to track these floats, and once in the water, they'll operate for months. Floats are one way of measuring deep currents, but recent technology has made another approach possible: deep-sea current meters. In this lab, meters are being given a final check before being attached to a mooring. The meters record the north-south and east-west components of currents, working in much the same way as an anemometer measures wind speed and direction in the atmosphere. The data is stored on magnetic cassettes. Once thoroughly prepared and checked, the meters are attached at anything from 500 to 1500 meter intervals on the mooring cable and paid out over the stern. The ship steams slowly forward, and the mooring is strung out on the sea surface, the whole thing being kept buoyant by floats. For a typical mooring, something like 4 kilometers of chain and cable has to be laid out over the stern. The number of current meters varies from site to site, but a typical mode mooring contained 4 or 5, covering depths from 500 to 4,000 meters. The top of the mooring is capped by a flashing light and radio beacon, seen here in the foreground, to help in the recovery when the mooring is eventually retrieved. The bottom of the mooring, over a ton of anchor, is the final bit to be paid out. With the anchor gone, the whole mooring is pulled slowly down. Everybody wondered whether they would ever see the equipment again. To see what happens as the anchor sinks, look at this diagram of the mode area. The depth scale is highly exaggerated. The heavy anchor and the glass floats work to pull the mooring into a vertical line, with the top beacon at about 500 meters below the surface. From their fixed position, the current meters record currents which move past them, and this, you'll recall, is the Eulerian approach to current analysis. On the other hand, so far floats move along with the water, and this lends itself to the Lagrangian approach. Ship time is very expensive. The arduous task of laying out the vast number of instruments continues day and night. This is what Walter Monk meant when he said the hell was instrumented out of this area. New instruments are tried, alongside older, better tried techniques. But what picture does it all give us? This analysis of the data, collected from the mode area over the whole period of the experiment, revealed water movements that showed the birth of a deep ocean storm. What we're looking at is a contour map of the 10-degree isothermal surface, which lies about 1,000 meters below the sea surface. This surface of equal temperature isn't flat, but undulates between hills, where the isotherm is nearest to the sea surface, and valleys, where the isotherm goes to its deepest. Warm water is less dense than cold water, so in the dips, where warm water goes deeper, we have a low-pressure region. Under the hills, where there is less warm water above, we have a high-pressure region. So in this way, we may view the contours like the familiar isobars on the atmospheric weather charts. And the currents swirl around the high and low pressure regions, just like wind in the atmosphere. The only difference is in the time and space scales between the atmosphere and ocean. The ocean moves much more slowly. As the weeks progress, the pattern of ocean weather slowly develops in a way rather reminiscent of the development of atmospheric weather. But even though the ships had returned to port, technology was still at work. Peter Rines, another mode scientist, explains.
Now, after the moat experiment was finished, everyone had packed up and gone home. They left some SOFAR floats behind because they were heard from land and there was no need of anyone out there. And these SOFAR floats drifted wherever they wanted to. In fact, in this case, they had stagnated for some months, and all of a sudden they spun into life. It circulated in a very strong eddy-like motion with speeds greater than a knot, which is a very fast flow for this part of the ocean. And it gradually worked its way westward until it hit a very significant bit of topography, the Blake Escarpment, at which point it shot to the south, again at very high speeds.
What causes these eddies? There are probably a variety of mechanisms, and I don't know the answer. But one thing is clear. These eddies are not the bearings that are being rotated by the general climatic circulation. They are much more like the gears that put momentum into the general circulation. In this sense, they are quite a bit like storms, which are not driven by the general circulation of the atmosphere, but are known to put momentum into the general circulation.
It's very difficult to apply simple mathematical analysis to the apparently random motion of this SOFAR float track, for example, which is caught up in an eddy field. It certainly can't be done with paper and pencil, but there's a powerful tool to help us, the computer.
Computers can be used to solve these equations step by step so that you can set an initial pattern of currents going, and you can tell the computer to predict tomorrow, the next day, and on into the future what these currents will do. This is how we use the computer. We take a piece of the ocean, like the Gulf Stream, we remove it in our minds from the entire complex bounded ocean. This is a computer simulation of an isolated Gulf Stream. The Gulf Stream, as represented here by its streamlines in the upper part of the ocean, where you see the streamlines bunched together, the flow is most intense, and the flow is always along the direction of the streamlines. And as time proceeds, it breaks into a field of eddies. They get bigger and rounder as time goes on, and the Gulf Stream has all but disappeared in the flow field. That's the shallow ocean. The different levels of the ocean are doing rather different things, though. If you look in the deep water, you see that we started with absolutely nothing happening, and in the same time sequence, this meandering motion up above has set off a regular train of eddies. It's part of this instability process. The train of eddies grows and evolves and develops into a pattern of big round eddies, rather sympathetic to the flow above.
The discovery of this mesoscale circulation of eddies has presented the oceanographers with a very tough problem. One way out would be to produce the ocean equivalent of weather maps. But the job in the ocean is much harder than in the atmosphere because the ocean eddies are so much more compact, so much smaller than the equivalent storms in the atmosphere. But nonetheless, there may be ways, possibly by the use of satellite observations, to produce such ocean weather maps, but we're certainly many, many years away from it. If you give up on this, it would be like if the meteorologist had given up on weather, and if he was satisfied to provide a pilot taking off from an airport with 10-year averages of February winds. Surely that wouldn't be a very useful piece of information. So we're left with a great challenge and no very good idea of how to go about it.